Hop.
So, and Romain Michon will talk about physical modeling libraries.
So, 15 minutes, huh, Albert? Perfect. Good morning, everyone. So I'm going to talk about the Faust Physical Modeling library, which I saw a lot of people already used during the conference. So I'm not sure if I'm going to introduce anything new, but at least if you never used it, you know, like it's probably a good introduction to it. So first, I'm going to talk about Faust and physical modeling in general, and just do a little history of Faust and physical modeling. So the first example of physical modeling in Faust was by Julius Smith, who implemented his virtual electric guitar and related effects. So all the slides that I'm presenting here are available online. I'll give you the URL at the end of the presentation, but you can follow the link if you want to check this out. So that's pretty cool. It's a project that Julius did, I think, in 2008 or 2009. You know, and you have a series of electric guitars that are implemented in Faust. And then all the audio effects that are now in the Faust libraries, but that were implemented as, you know, standalone Faust objects. This kind of gave birth to this app, which was released about 3 years ago now. I think it's called GeoShred. It is made by Julius and two of his buddies in California, and it's an app that allows you to play electric guitar on your iPad. It's very nice. Jordan Rudess uses it for almost all his concert with Dream Theater, you know, and other famous artists, and it's available on the App Store. And this is running Faust in the background. It's, I think, available for $24, you know, like, which is probably above the budget of some people here. But, you know, it's a very, very cool product, and it's probably one of the most advanced example of Faust code in a way, because it has like very advanced physical models as well as audio effects, you know, and everything is implemented in Faust. So GeoShred is 3 years old, you know, but in between I worked with a few other people on this thing, which was the Faust SDK. The Faust SDK was a comprehensive implementation of the physical models that were available in the original SDK, which was in C++. It was just a basic translation of the SDK in Faust, you know, like, so we just took the SDK examples and then we ported them to Faust, you know, like, and we didn't really do more than this. We also fixed some models that were not completely accurate, and we also did some archaeology on old Next machines at Karma that implemented physical models, you know, like from the 90s, and that were never ported in C++, you know, like, so that's the case of the piano physical model. I think the bass guitar physical models, all these things were not available anywhere except on this Next computer at Karma. So that's kind of an overview of physical modeling in Faust, you know, at least on our side. Maybe there are projects that we don't really know about, but oh, and there's of course Ed Bertel's Synth Modular, which I'm going to talk about now. So now let's talk quickly about existing environments for physical modeling of musical instruments. So here I'm really talking about high-level environments that allow you to make virtual musical instruments that are based on physical models, not necessarily in Faust, but environments that allow you to take say a string, plug it to a resonator, and construct new musical instruments to be run on a computer. So Modal is probably the most famous one of them. It's been developed by Eurocam for many years now. Cordis Anima was developed by Acre in Grenoble. And Synth Modular is also based on Faust and is developed by Ed Birdle at Louisiana State University. And all these environments use different physical modeling techniques. Synth Modular uses a combination of waveguides, modal physical modeling, and also mass springs. Cordis Anima is only mass and springs, and Modal is mostly modal synthesis of some finite element analysis as well as some waveguide, I think. But so in Faust itself, we didn't really have any environment to do high-level physical modeling just by plugging different instruments, elements of musical instruments, and that's what the physical modeling library is for. So we introduced these two new tools about a year ago: the Faust Physical Modeling Library as well as Mesh to Faust, and together they make the Faust Physical Modeling Toolkit. So one of the main feature of the Faust Physical Modeling Library is that it introduced a bidirectional block diagram algebra, and that is something that is really important, because when you do physical modeling of musical instruments, you want to couple elements to each other. So let's say that you have a string, a bridge, and a violin body. If you connect them together, their waves are not going to go in one direction. They're going to go in two directions, because waves are going to be transmitted to the body of the violin, but then they're also going to be reflected, and so in order to be able to implement this coupling, you need to be able to implement things in a bidirectional way. So in Faust, it is currently possible to do it, and that's what this is here. So in this case, we could imagine that A and D are implementing an object, and which is connected bidirectionally to B and C. And in Faust, we can just do this with feedback. Now, the problem with this is that it is not modular at all. If we want to do this, we have to implement the whole thing from scratch, and we can't just say that we want to connect AD to BC in a bidirectional way. So if we want to make an AD module and a BC module, we just can't do it, because we have to write everything on the same line. So we introduced this new primitive, which is the chain primitive, and the chain primitive allows you to create this type of bidirectional connection between blocks. So in the Faust Physical Modeling Library, blocks have 3 inputs and outputs. The first 2 inputs and outputs corresponds to left-going waves and right-going waves, and that's what we see here. And then we have a third input and a third output that can be used to carry a signal to the end of an algorithm. And that's something which is very important, because, for example, if you have a string and you want to put the pickup of the string at the middle of the string, then it means that you need to retrieve the signal of the string at the middle of your chain, basically. And if you want to carry the signal from that string down to the end of your algorithm, you need to have some kind of bridge to do this, and that's what this third input and output is for. So here we have a very basic example of how the chain primitive works. It allows you to use the connection operator in Faust, except that in this case it is a bidirectional connection. So empty block here has 3 inputs and 3 outputs. It's connected to a waveguide, which is just 2 delays in parallel, and then connected to another empty block. And you can put as many elements as you want within this chain. So that's an example of an empty block. An empty block has nothing in it. It's basically just 3 signals in parallel, one going in one direction, one going in the other direction, and one being the output signal. Then you can also create terminations within this environment, because that's something that you usually need to do waveguide physical modeling. So you can use those primitives to do this, and this is also completely compatible with the chain primitive, so you can really put all these things together. So I'm going to show you a few examples of this very briefly, because I need to talk about something else after this. But here is an example of a Karplus-Strong algorithm, and here is how we implement the Karplus-Strong algorithm. So you will see that we have KS chain here, and that's directly from the Faust Physical Modeling Library. And KS chain has terminations on both sides. So on one side there is just an empty connection, so it's just a signal, and then on the other side there is a reflection filter, and the reflection filter is the usual reflection filter for Karplus-Strong, which is basically just a 1-0 filter. And then here we have a chain of elements. In this chain of elements we have an input, which we can use to feed an excitation inside the loop. Then we have a string segment, which is basically just a waveguide. So two DLL lines in parallel, and finally we have an output here, which allows us to listen to this very specific point to retrieve the signal and then bridge it to the third output of the block, which is the output. So that is a very, very, very basic example. So see here we're doing some tuning by hand. You know that when you do waveguide physical modeling, you always have to tune things by hand, because all the filters that you use inside your loop tend to add delay, and because they add delay, they change the length of your string a little bit. So you always have to tune things by hand. And that's how it works. So in the Faust Physical Modeling libraries, we completely re-implemented all the Faust SDK. So all the examples from the Faust SDK are now completely modular and re-implemented in here. And we also added many, many, many new models. And I'm not going to give you an exhaustive list here. This is all in the Faust distribution. So if you want to have a look at this, you can just check it out. Now I'm going to talk very briefly about this other tool, which is part of this whole toolkit, which is called Mesh2Faust. And Mesh2Faust generates physical models compatible with the Faust Physical Modeling library using finite element method. So the idea behind that is that if you are using the Faust Physical Modeling library, you're going to find musical instrument bodies and strings and etc. But then there is something that is missing. So, for example, you want to implement that very specific violin body or resonator. Then that's what you want to use. And for this, I'm going to give you an example of a Marimba physical model, which is basically based both on the Faust Physical Modeling library and Mesh2Faust. So if you go in the Faust distribution, in libraries, models, Marimba bar, you're going to find an SVG file, which is just a 2D drawing of a Marimba bar. So what we did is that we implemented this tool in Inkscape that allows you to turn that into a 3D model, which you can then open in OpenSCAD. So from this 2D model, you then get this nice Marimba bar. OpenSCAD is this CAD software. It's open source. It uses code, and what we did here is that we went from Inkscape to OpenSCAD to get this 3D model. Once you have the 3D model of the Marimba bar, you can open this. Oh no, not here. You can open this in MeshLab and probably do some reworking on the mesh to make sure that it's completely balanced, and eventually through a script which you have here in build, and that I'm going to try to open in Atom, I guess. You can call Mesh2Faust, which is what we have here. So this is kind of small, but this is just a terminal application, and you give it the 3D model, which is your Marimba bar. Then you can set the material properties, the position of excitations, and all these things. And in the end, what you get is a modal physical model of the 3D model that you gave it, basically. And you can have a look at this actually in the Faust Physical Modeling Library, because we already have this one here. So if we do a search for Marimba bar model, there we go. Here it is. So we have our Marimba bar model, which is based on the 3D model that I just showed you. And it has a series of frequency ratios, a series of gains, and a series of T60s that were all computed using finite element method within Mesh 2 Faust. So the whole idea here, is that because we don't have this specific Marimba bar already in the library, then we just generated it using Mesh 2 Faust. And then eventually what we can do is just assemble all these things together with tubes that are available in the Faust Physical Modeling library. So if we look at the Marimba bar Marimba model, the Marimba model is just the Marimba bar model. So the bar that we modeled with Mesh 2 Faust connected to a tube, and that's our Marimba. How does this sound? I think I probably made a few examples of this, and it should be right here. Presentation, Faust Physical Modeling Library. So I probably need to plug the audio too, which I haven't done, sorry. And probably start Jack, because I converted those things as Jack applications, and I bet Skype is not gonna like this, but doesn't matter. Okay, so here we have a clarinet example from the Faust Physical Modeling Library. You'll see that some examples are called MIDI examples. Other examples are not MIDI. The one that are not MIDI just allow you to control the different physical parameters of the physical model. So here we're just controlling pressure. The MIDI version is MIDI compatible. So it has a trigger, and then you can use it with a MIDI keyboard, and you can do polyphony and all these things. And here is the Marimba bar model that I just showed you. So, well, this is 65 hertz, so it's pretty low. So we're probably missing some bass here, but well, we can hear the resonance from the tube. It's all there. We can control the strike position because we specified that in the model that we generated with Mesh 2 Faust. And that's pretty much how it works. So I will stop here. If you want to know more about all this, you can check this website here. My slides are available here. All these tools are available in the Faust distribution if you want to try them. Just to warn you a little bit, Mesh 2 Faust is not super straightforward to compile, so you should be ready for this. And it's not really our fault. It's because Mesh 2 Faust relies on the MKL library, which is the Intel math library, and it's free but not open source. And depending on the platform that you're using, it might be a giant pain to install. What? It is, yeah. So if you're an Arch user, you're in luck, because then it's very, very straightforward because it is in your package manager. If you're using a Mac, you're fucked basically. But it works. You can do it though. And then if you're using Windows, then it's even worse. So everyone should use Linux here anyway. But any questions?
Do you have any questions?
I'm curious, what's your favorite model? Which one sounds best? Which one sounds most fun? I think the clarinet is probably the one that sounds best. I would say, I don't know. The problem with physical modeling is always the same. Like you have those instruments and they have all these parameters that you need to control at the same time. and your model is only going to sound good if you control your parameters in a way that makes sense. You know, like in the case of the clarinet, I think we tuned pretty well the envelope that controls the pressure and function of the mouth position on the mouthpiece, you know, and all these things, and there is not much that can go wrong, and I think that's why that's the one that sounds the best, you know, like, but it's, I mean, those things are, like, I don't know if you guys know about the Swarm audio engine. It's this plugin which is made by this company in Italy, and they have a violin physical model in it. We saw the physical model, like we saw the code. You know, it's basically pretty much the same as the one you have here. And it sounds so good. It's like if you don't pay too much attention, it really sounds like a violin. You know, like it's very hard to tell that it's not a real violin. You know, and in terms of the algorithm, we kind of have the same thing here. You know, like but they spend months and months and months, you know, like tweaking it and making it sound good, which is something that we never do. Because once it works, you know, and then you're happy. So. Yeah. Yeah, there is an insane control layer above the DSP algorithm. So between the user input and the sound synthesis, then there is this big black box that just does the right thing, and we don't really have that here, of course, because yeah, it's the missing part, and yeah, master thesis, yeah, but all the models that are here, you know, they're pretty much the models that you find anywhere else, you know, like even in most commercial plugins. It's just that I didn't spend time making them sound good, so